Okay, let's unpack this. So you've definitely seen large language models generate those long, detailed chains of thought.
Especially for things like complex math problems.
Exactly. And
Yeah.
it looks really smart on the surface, but how do we really know if they're genuinely thinking and not just, I don't know, mimicking a pattern?
That's the core question, because judging them by just the final answer or even the token count, it just feels totally superficial, right?
It does. So our mission for this deep dive is to get past that surface level and
Yeah.
actually map the LLM's internal cognitive structure.
Precisely. And for that, we're looking at a new framework called ThinkARM, which stands for the Anatomy of Reasoning in Models.
ThinkARM. Okay.
And it takes this idea, Schoenfeld's episode theory, which was first developed to watch how human students solve really hard math problems, and applies it to an LLM's reasoning trace.
So we're basically putting the model in the chair, like a student, and just documenting its workflow. But that framework has, what, 8 different episodes? Read, analyze, plan, implement. That's a lot to track.
It is, but you can sort of simplify it. ThinkRM abstracts those 8 down into 3 core phases. You have your setup steps.
The read, analyze, plan part.
Right. Then you have the execution step, which is just implement. And then, most critically, the metacognitive steps.
Explore, verify, and monitor.
Exactly. And the hook here, the really interesting part, is that when you map this out over time, you see this measurable, reproducible, call it a cognitive heartbeat.
A heartbeat that's completely different for models that truly reason versus those that just, follow a script.
It really is, and that heartbeat unfolds in a very predictable way. The initialization is all front-loaded, dominated by those setup phases you mentioned.
Makes sense. You have to read the problem first.
Then you see the execution phase, the implement part, the actual calculations. It peaks right in the middle of the response. That forms the backbone.
And then I'm guessing as it gets closer to the end, those metacognitive steps, the self-checking, starts to surge.
That's it. It signals the model is regulating its own process before giving the final answer.
Okay, wait. You have verify and monitor both happening towards the end. What's the conversational difference between them? They sound similar.
That's a good question. Think of it like this. Verify is checking your work. Did I do that calculation correctly? Monitor is bigger picture. It's checking your strategy.
So is this even the right way to solve this problem anymore?
Exactly. And that's where we see this huge structural gap between what we're calling doing models and thinking models.
So the non-reasoning models are kind of like that student who just grabs a calculator without ever really analyzing the question first?
That's a perfect analogy, yes. They spend almost all their time and energy just executing, just on implement. It's a very rigid feed-forward path.
But the reasoning models.
They're much more balanced. They dedicate a lot of time to analyze, and crucially, they show these frequent iterative feedback loops. The model will go from exploring an idea to monitoring its progress and then back again.
That internal self-checking. That's the signature of actual thinking. Okay, so if that's the key, let's drill down on correctness. The sources say that the explore episode is where things either go right or horribly wrong.
It's the critical branching point. When the model hits a point of uncertainty, that's what explore really is. A successful solution is almost always associated with routing that exploration into monitor.
Into self-reflection.
Or back into analyze for, renewed conceptual work. It literally stops to think.
And conversely, if it's failing, we see these routing breakdowns.
Yeah.
Like the model's in the middle of calculating and then suddenly jumps all the way back to just rereading the problem.
Yes, or it just gets stuck in this high-ratio explore loop without ever landing on a stable solution. We can basically diagnose its failure mode just by watching those transitions.
It's like watching a film of its thought process.
It really is.
So if a healthy model needs all these self-checking steps, what happens when we force it to skip them? In the name of speed and efficiency.
Well, efficiency is not behaviorally neutral. We found that methods designed to shorten responses, things like ThinkPrune, they don't achieve that by uniformly trimming tokens.
So it's not just making everything a little shorter.
Not at all. It's selectively suppressing the conceptual and the evaluative episodes. It dramatically cuts the budget for verify and analyze.
So speed comes at the expense of that internal self-checking.
And at the expense of the entire reasoning structure, really.
That feels like the core takeaway here. ThinkARM gives us a way to analyze LLM thought processes with the rigor of a cognitive scientist. It proves reasoning has a measurable structure.
It completely shifts the evaluation. We're moving from, did you get the right answer, to, did you think about it correctly?
It's about auditing the internal process, not just the output.
Exactly.
Okay, so a final thought for you to chew on. We've just seen how the push for efficiency makes LLMs suppress verification steps in objective math problems. If we took this framework and applied it to LLMs tackling something messy, like political or ethical reasoning, where verification means considering nuance or monitoring for bias, what critical cognitive steps do you think would be the first to go in that relentless pursuit of speed?